Started. So good morning, everyone. I hope you are keeping warm from where you are. It's cold here in Raleigh, and from other people around the world, I hope it is even colder. So this is our very first AERPAW webinar. Even though it is set up like not like a webinar, we are learning. It's the first one. And they say, if something is important, you get to do it until you learn to do it better. So we are learning and we'll do it better next time. We will set it up as a really webinar, not a Zoom meeting. But for this first one, you're here, and thank you so much for attending this. As you saw, our very first webinar is 101. It's AERPAW 101, and Ismail will share with you what AERPAW is, what it can do, and what it cannot do. And we'll also answer your question. We have our outreach coordinator, Sulan. She will also be monitoring our chat for any questions. And we will answer those as Ismail is presenting, and some of those that we cannot answer, Ismail will answer them at the end. And we will take questions at the end. Help Ismail, you leave some time for questions and answer, okay? So we can take them at the end. And with that being said, Ismail, the floor is yours.
All right. Thank you, Margaret. I'm a bit under the weather, so I hope my voice is not going to disappoint me. But let me share my screen. So, as Margaret said, this is the first webinar, and what I meant to do is, let me switch the screen. Or maybe I'll just move to here. Just a second. Here again. Hopefully this is good now. So this is AERPAW 101. So I'm going to do an overview of AERPAW and opportunities, and this is a very generic presentation. If you have questions, I can even take them on the go if you have burning questions. Otherwise, we can leave them to the end. And this was what I meant to present. So I'll just motivate and give an overview of Power Platforms. I see some of you, some familiar faces. So some of you are very familiar with, I guess, some of these concepts like Aloysio, Alpan. So it may be repetition for some of you, but hopefully there will also be new things. I'll overview AERPAW, talk about our sample experiments and data sets. These are sample experiments and data sets are what we hope some of you can use. We have started seeing more and more papers, especially with data sets that we have been releasing, and also using some of the sample experiments. And if depending on the time and interest, I have some representative results in the end. And I can also share this with all of you. Maybe I didn't think of having a chat, having a link, but maybe in the end I'll try to share this in the chat. So let's start. So this is just very broader motivation. You all know that at universities we mostly do fundamental research. In corporations there are products. You know well the value of death. But this is especially for the wireless and drone area. This has been widening. There are hundreds or thousands of papers coming up with very simplistic models. I have 3 quick quotes, one from Feynman. It doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. And if you search for it in YouTube, he's actually talking about this in his lecture, so it's pretty nice. Another one is from George Parks. All models are wrong, but some are useful. So he's a statistician, and he's talking us in the context of probability models, but it also applies more general to other models too. At the end of the day, models are models, so they don't always characterize certain behavior all the time. There will be variations from that, but if it's a wrong model, I mean, those variations will be really high and they won't work in practice. And finally, Grace Hopper computer scientist and mathematician, one accurate measurement is worth 1,000 expert opinions. So we have been seeing this more and more. Actually, I had my group meeting right before this meeting. We are observing a lot of interesting behaviors based on the data that we have from the drone. We are trying to, I'm talking about like fitting path loss, shadowing, or fast fading models, but depending on the altitude, orientation, tilt, or even the Doppler, if the drone is hovering or just starting to move. So there are many interesting things happening, and it's great to develop even models for characterizing all those. And to fill this gap, NSF, what we need is we need programmable test beds that is accessible to broader research community, which is you are part of it. You all may have your own experimental equipment and facilities, but I also had before AERPAW my own drones and USRPs, but the experiments I tended to do were very small scale, but we need larger test beds that can be characterizing more realistic environments and more capable equipment and features. And NSF introduced the Power program back in 2018, 2017, I believe, and they funded 4 platforms, Powder, Cosmos, AERPAW, and ARA, and we were funded in 2019. We are actually finishing our 7th year, so we are trying to get one last no-cost extension during the summer. So at the end of August this year, we are going to finish our main project. We have a CERC award that we are sustaining the platform for another year or two, but we are still supporting all the NSF funded researchers. So if you have an experiment, if you have a project funded by NSF and want to use AERPAW, in the canonical experiments, I'll talk about what that is. We can support your experiment for free. We have a large team, many researchers, many universities, and we had funding from equipment donations from many different companies. So where is AERPAW located? It's located at 2 different sites nearby NC State. We have a Centennial campus site. We have 3 fixed nodes there with USRPs. I'll talk about what is there in the fixed nodes in a minute. We have our Lake Wheeler field farm site, which is about 7 kilometer square area, where we have 5 towers and the drone operating center. This is the second site is where we fly the drones, and actually you fly the drones if you program AERPAW, and then you can fly them in any way you want, and also in an autonomous manner. We don't have any restrictions except a few, the minimum altitude, the maximum altitude, the speed of the drone, and the geofence. I guess these are pretty much all the restrictions. Other than that, you can have all kinds of different crazy drone flights that you want based on what the drone is observing, and then we support all of those. If you send a command to our drones that doesn't pass our filters, we can stop the experiment. So we have all the safety checks in place. This is another map that shows our 2 sites. Centennial campus is our engineering site. If you are interested not primarily on drones but still want to do some basic testing between different fixed nodes, you can test them here first. You can configure them as base stations or UEs. We have 3 towers that can behave in any way you want based on the way you program the USRPs. And this is the Lake Wheeler site that's about a 10-minute drive from our Centennial campus. And these fixed nodes, they have USRPs in all of them. They have key site array sensors in 5 of them, 1 of them in Centennial campus and 4 of them in Lake Wheeler. I'll talk about what you can do with each of these different hardware. In Centennial campus, we have Facebook telegraph radios at 60 gigahertz. These 4 here at the bottom side of the map, they include Facebook telegraph radios. We have LoRa gateways, I think, in 7 of the 8 fixed nodes. And we have an Ericsson base station in 1 of the fixed nodes, which is Lake Wheeler 1, you see here. In addition to fixed nodes, we have vehicles and portable nodes. And vehicles are what you can move except for helikite, which cannot control where it goes. It's tethered and it kind of goes sideways based on the wind. But the others, you can program them any way you want, either giving fixed waypoints, or they can also fly autonomously based on what they're observing. And we have, I believe, 3 large air-powered multicopters. LAM is a large air-powered multicopter. SAM is a small air-powered multicopter. So we have 3 LAMs and 7 SAMs and 2 UGVs. I think it's going to be 3 very soon. And we are also working on a HAM and a TAM, so heavyweight air-powered multicopter and tiny air-powered multicopter. So these have different payloads, and the other 2, they are not ready yet, but depending on the type of experiment, you may want to choose LAMs or SAMs. SAMs, they don't carry USRPs, but they can carry like a mobile phone or a LoRa sensor or a USB dongle. And there is a Latte Panda compute node in the SAM, in the portable node in the SAM. It's a smaller portable node, and the LAM carries these small USRPs that you can program in the digital twin that I'll talk about soon. And it also has a Intel NUC computer, which runs the Linux containers, same as the Latte Panda in the SAM. And these the portable nodes, they can be taken from one UAV attached to another UAV. You can carry them in a cart. You can attach to the helikite or the UGV. I'll show examples of that maybe in the coming slides. But you program them in the digital twin that I'll talk about soon. Before I go to those details, I just want to show this paper from Cornell. This is not related to AERPAW, but it talks about agentic UAVs. You may have heard of agentic AIs, which are, I'm sure all of you have heard. But agentic UAVs, they kind of, in a similar sense, they function as intelligent systems capable of perceiving their environment, making complex decisions, and executing actions that align with mission objectives in a dynamic setting. So this aligns greatly with what we have in AERPAW. So we don't only have communication capabilities, but we also have autonomous navigation capabilities. So UAVs can make their own decisions on not only where to go, but also what to transmit, how to adapt their parameters to, for example, make handovers, and this can be coordinated with the ground base stations, right? So I think this is a great overall fit, considering all the power platforms. This autonomous navigation coupled with wireless adaptation is our value add among all the power platforms. And these are some use case examples. Not all of them we can support yet, but we are keeping adding new features. And we are doing competitions pretty much every other year. I'll talk about those competitions in the coming slides, but they are targeting some of these use cases. One example is, for example, there is a UAV that collects data from a number of sensors in the field, but it has to decide how to fly, where to go first, and how much to wait there, and so on. And we just wrapped up our AERPAW Autonomous Data Mill competition last fall. We had 22 student teams registered, and 16 of them submitted their solutions. These are all teams across different universities. We only have 2 NC State teams. And then we deployed 11 of those solutions in our testbed for the final round. Another example is search and rescue and localization. The drones, one or more drones, they can fly to autonomously localize a target. One use case is search and rescue, but there can be other use cases as well. We wrapped up our AERPAW Find a Rover challenge 2 years ago, and we have all the details in the website. I also talk about them in the later slides a bit more. But there can be other use cases. There may be flying base stations that are serving a disaster area and autonomously position themselves so that they serve that area in the best way. We have a sample experiment for a flying 5G base station. So you can use that sample experiment and you can deploy your own autonomous positioning, autonomous navigation algorithms while using 5G, for example. And there can be others. We don't support beamforming yet. We hope to get there, but we ran out of funding. We have our hardware, but we didn't open it for external use. You can have UAV to UAV communications, UAVs are cellular relays, and you may have multiple UAVs that are sharing the spectrum. You're actually planning the third competition to be on spectrum sharing. Hopefully we will release it by late fall or early spring. One of our advantages is we have a digital twin environment where you can program your experiments in a completely virtualized environment. And this is not a simulation. You are developing your software that will eventually get deployed in the real testbed. So you are programming the software containers that will run at the drones and at the base stations. So if you have an experiment with, let's say, 3 base stations and 2 UAVs, then you have 5 software containers that you are programming. And we have sample experiments that are already tested and ready to go. You can start with those sample experiments, and then you can expand them to deploy the algorithms and research that you want to proceed with. And there are several papers related to this if you want to read more about the details of the digital twin. But especially, I'll jump to this one and I'll come back to the previous slide. One of the main features of the digital twin is there is a sophisticated IQ wireless channel emulation environment, which makes it possible for multiple software containers to communicate with each other. These software containers, as I said earlier, can be at fixed nodes, then they might be running the network software, radio software, the vision and radar. We don't support them yet. We hope to add them in the future, even though they show here this is more like futuristic. But we support IQ wireless channel emulation and software in the loop vehicle emulation in the emulation environment right now. So you, as you fly multiple drones and as they communicate with the base stations, they interact through this additional container which accepts IQ samples, and then it's basically it's emulating as if the drones are flying in a real environment, and then captures the interference effects. You can try handovers and so on. So all whenever one of these devices transmit, like the UAV transmits, then it's received by all the other nodes that passing through this channel emulation environment. And it's been more than 3 years. One of another AERPAW Kopyay Mihai CK2 students has been working on this, and it will be made open source if any of you are interested to use it in the future. But that's the digital emulation environment, and this is helping to support all the full stack protocols like OAI or SRS-RAN running 5G at the base stations and at the UEs. But before getting there, we also, if you're interested, we also have simulation environments that is doing some abstractions. For example, it doesn't run the whole full stack protocols, it just calculates the RSRPs for a base station. If you're just interested in signal strengths and trying to develop a navigation algorithm, you can develop your algorithms here, and then you can deploy them in the emulation environment with all the real containers. And then once you develop your solution, if you're interested, we have a sandbox environment where we have now a hardware emulator, hardware-based channel emulator, which is Keysight PropSim, where we have, I believe, 2 UAVs and 2 fixed nodes. So if you want to scale more than those, you cannot do them in the sandbox, but you can do them in the digital twin. But in the sandbox, if you're interested to capture hardware impairments and do testing in a more realistic environment, you can deploy it in the sandbox. We haven't opened this publicly yet either. We were hoping to do this by now, but we are hoping this will be like this summer. We will also open this for public access. And then you can pass the containers from one to other all the way to the testbed. So once you are comfortable with your development in the digital twin or the sandbox, you can deploy this in the testbed environment. And before getting even to this, any of this, like the emulator or MATLAB, you can connect your portal and initiate your experiment. I think there will be a separate webinar in the future, but I'll just quickly show you how easy it is for you to initiate an experiment. You just go to aerpaw.org, go to experiment web portal. By the way, we have a detailed user manual as well with LLM instructions. I might come back to this depending on the time. But then in the experiment web portal, you just log in there. You're using your institutional credentials. Most likely your university will be located here. You log on using your institutional login and password, and then you come across this screen. I think you will first need to initiate a project, I guess, and then it has to be approved. But once you initiated an account, then you can request to join one of the other projects, or if you have a PI, if you are a PI, you can initiate your own project. If you are a student working under a professor, you can ask your professor to initiate a project and then join his project. For example, I have my course projects here, like last fall. I had several students doing projects under my EC 578 course. And I have others more for research, students doing handover experiments or OAI, ORAN, and so on. So you can, again, if you are a student, then you can ask your faculty, your advisor to initiate a project under this, and then you can just join that. And then you can start using one of the sample experiments from here directly with SRSRAN or OAI. I'll talk about those a bit more later. I'm sure there will be more discussion about this in one of the future webinars, so I'm not going into details, but I wanted to give you a sense of how you initiate a project, going through the portal, configuring your project, and if you ask, maybe one last thing I will quickly show, if you go to the top and click resources, you can see all our fixed nodes and UAVs and portable nodes listed here. So you can pick and choose from these resources, and each of them will be a container. And if you choose, for example, 2 LAMs and 2 fixed nodes, then you will be assigned 4 containers in your digital twin environment that you can start programming, and then you can reuse these sample experiments. You can inherit them and start developing immediately. Again, I'm sure there will be more dedicated webinars on this in the future. And as far as the AERPAW vehicle software, like I said earlier, we have filters that we make sure that you are not doing anything that's not safe, like flying outside of the geofence, flying at a very high speed that may be risky. But other than that, you develop this vehicle control application that sits over the AERPAW vehicle library and other standard open source drone software that controls the drone. So whatever you develop in the digital twin, it is what is flying the drone in the real testbed. So the drone pilot is not flying the drone, it's a safety pilot. It's just monitoring what's going on. If there's anything risky, the pilot can take over the control and land the drone back safely. But other than that, you are the software that you develop in the digital twin here, it flies the drone, running at either the Intel NUC or the Latte Panda compute node. I'll just show a couple of photos. This is one of the fixed nodes, or first fixed node, Lake Builder 1, and you can see the enclosure next to it, which has a lot of USRPs and servers, RF front ends. This is also our Ericsson fixed node. You can see the 4G and 5G sectors. We have 2 sectors of 120-degree angle, as you can see from the antennas here. On the top are the USRP antennas. So these are what are transmitting the either OAI or SRSRAN or GNU radio, etc. code that you develop in your digital twin and communicating with the portable node antennas that are located at UAV. And this is a close look into our UAV. You can see the portable node attached to the UAV. You can take it and attach to the UGV, like in here. So you can see 2 antennas here. One of them is for transmitting, the other is for reception. They are separated apart because we don't want coupling in between them. And we have a 2x2 version of this too with B210 USRPs. And you can kind of see the Intel NUC computer here. In addition to this portable node, we have many other things happening here. You can see the RC antennas. This is how the pilot can take control of the drone if it's needed. You can also see the cellular modem. So we are always connected to AT&T's 4G network. This is our back channel, so we can take control of the drone and the whole experiment through our cellular link if needed. In addition, this is in addition to the RC connectivity. One of the other aspects of this is we don't give access to this by default, but if for some reason you want to pass information between the drones, we have direct connectivity to all the drones, so we can pass information from this drone to another drone through this cellular side link. So this cellular link obviously goes to AT&T's base station and network, and then comes to us, but then we can pass it back to another drone if for some reason you are interested to use that feature, for example, for edge computing type of experiments. And this is our small portable node. You can see the latte panda, and this might carry, as I said earlier, either like a mobile phone or a USB dongle. That can be, for example, QuakeTime modem for 5G or rover, and all of this are programmed in the digital twin. I want to emphasize that. So the way that any of these, including the small UAV multicopter or SAM, you can program in the digital twin so that they adapt to variations in the signal strength or latency or whatever wireless metric that you might be interested in. And this is our helikite. We have done 6 experiments with it so far. It's a bit more expensive to fly because helium is expensive. Helikite is a helium balloon kite, so it's not only a balloon, it also behaves like a kite. If there is wind, it doesn't go sideways very quickly, a bit more stable, but it costs about $2,000 just to fill in the helium for this balloon. But we have annual experiments as part of a festival. We attach our portable node and we collect all those spectrum data. So we have a drone operations center. We haven't populated this mast yet, but we hope to include additional SDRs on top of the mast. And we can also take this to other places. And we have a OTEC. It's not on the one on the left, but the main equipment is the one on the right with the Keysight equipment for testing. So I'll skip these. And we have a lot of users, so this is a bit outdated, but especially some universities like NYU and University of Missouri, they are using a lot. NYU is using AERPAW for educational purposes, and Margaret is working with NYU to extend this to other universities. And maybe some of you are already in touch with Margaret on this to use AERPAW digital twin for teaching, so for supporting your teaching efforts. So maybe I'll stop here and see if there are any intermediate questions. It's already half an hour. Maybe I'll try to go maybe another 10 or 15 minutes depending on the time. But are there any questions so far? I see in the chat. Okay. No questions so far. All right, so I'll keep going on. So this is the list of the sample experiments that I was showing in the user manual. So as far as what we call the canonical experiments, which are primarily with USRPs, we have 4 different types of software that we are supporting, and they are available through our user manual: SRSRAN, OAI, GNU Radio, and UHD Python scripts for spectrum monitoring and IQ collection. We keep adding new experiments when possible. Actually, there are some other experiments that I realize I didn't add here. But these are canonical experiments, meaning that you can use the digital twin from beginning to the end to develop and test all your experiment. And then you can deploy it in the testbed. So this obviously includes the USRP software, the SDR software that you see everything in the red boxes, but it also includes the drone control software and the wireless traffic software. So I'll come to those 2 later. But in addition to these, We have a number of other hardware that you can use. One of them is KeySight array sensors, and these are deployed in 5 of the 8 fixed nodes we have, and you can access them in real time. They are somewhat similar to USRPs, but they are only reception. Their antenna pattern is a bit better. They have a better omnidirectional antenna, and one of their strengths is they have a commercial KeySight array sensors. They have a series of commercial software that you can use for monitoring the spectrum in real time and logging it, or for classifying signals. You can train the signal signatures, and then you can classify them. For example, if you're interested in a particular type of signal, it might be a signal from, let's say, a DJI drone. You trained it initially using KeySight array sensor, and whenever it shows up again and it's seen by one of the 5 sensors, that reception can trigger localization, which is the third experiment. So you can start localizing that signal using all the 5 array sensors. Actually, maybe 4 of them, because one of them is pretty far away in our Centennial campus. But there are very interesting software. I mean, we have a lot of details in our user manual. If you're interested in this, you just do a remote desktop to one of our computers, and we can. The procedure is listed under the user manual. We have a lot of additional sample experiments with Ericsson, Android, LoRa, and cellular modems. And I saw Asokan earlier, so Asokan developed a lot of these. But the main experimentation mode with these is to log data. So we cannot change the Ericsson base station configurations. It's pretty complicated for us, but you can log like RSRPs, or even if you are using, we also have a KeySight Nemo, for example, or PowerPrints Android app. These are software that run on on one of the UEs, and then they can log a lot of network KPIs, including, for example, channel rank or latency, or especially for KeySight Nemo, we have a large number of parameters that we can log. And then with all of these, you can still have autonomous flights. So you might be observing some KPIs from the network, and then the drone can decide how to fly. So you can program the autonomous navigation part of your software using your digital twin, but then you cannot program the radio part in the digital twin. And this includes also LoRa. So we have LoRa gateways, and you can get measurements from LoRa. I think it's our mostly populated equipment after USRP. So 7 of the 8 fixed nodes, they have LoRa. So if you're observing LoRa signal strength from towers, you can change, for example, how the UAV flies in an autonomous manner. And in addition to those radio software, so all these were radio software, we also have vehicle software and traffic generation software. For traffic generation, we support Ping, IPERF, and AmGen. You can come up with your own traffic generation software and deploy it, but these are the ones that we tested, and they are available for you to use immediately. But if you're interested in testing a video type of traffic or some other statistical traffic behavior, you can generate your own and test those. We also have a number of vehicle software that can be fixed waypoints, that can be multiple vehicles, that can be autonomous flights. So the sample experiments for all those are in our user manual, and then you can pick and choose from those. So if you want to do an experiment, let's say with LoRa and autonomous navigation, you pick the radio software, you go to autonomous navigation, and you pick your traffic generation. Traffic generation doesn't apply to LoRa. So all these, they apply to USRPs. And then you can test your experiment in the digital twin. And then you interface with a screen like this for your drone flights. 1036. Next up, I have some example experiments. This is just one example experiment. I have more, depending on the time I can go into some details. But you can see here, this is from VTC 2024, the drone flying on a line and running 4G and 5G full stack protocols. And you can see the distance that's between the drone and the base station located here. This shows bandwidth, but this is actually throughput. And all of this is deployed in the digital twin. You see that the throughput does not just follow a linear behavior. There is a lot of fluctuations, and we are working on actually for the 5G. We have been working on comparing this with the field experiment. So hopefully we will have more results comparing digital twin and field experiment soon. But you can see the throughput is higher when the drone is closer to the base station, goes lower, and then it goes higher again. And again, this is all based on digital twin experiments with SRSN, I believe that was. Sorry. And I'll briefly talk about our two student challenges. The first one was find a rover challenge. Okay, it's in here. So what we did here was we have hidden a UGV, unmanned ground vehicle, in this green box, and the experimenter or the competitor doesn't know where it is. And we do this 3 times actually in practice. One of those locations was outside of the blue box where the UAV can fly, and the 2 other locations were also within the blue box, so at the intersection of green and blue boxes. And just based on the signal strength, the UAV is supposed to localize the UGV. So that was the goal. It may look simple, but we are just relying on signal strength, which is fluctuating significantly. Like you can see here, just on the order of a couple of meters, your signal strength may change like up to 50 dB, which is huge. So there is a lot happening related to multipath, shadowing, and antenna effects, and so on. And then the UAV can decide how to fly. So there were some teams who used fixed trajectories like this, and they didn't optimize the trajectory of the UAV. There were some other teams who optimize where UAV flies based on what they are observing on the signal strength. And the second category, they performed much better. And these are the 5 finalists. So these 2 teams, they use fixed trajectories, but the others, depending on what they're observing, like University of North Texas team, for example, they start with a bigger triangle, and based on what they're observing, they narrow down the triangle, and you can see the UGV is this red triangle. They are localizing it accurately as they keep collecting more data. NYU team, they do the linear flight, the 2 lines first, and then they have some information, and then they decide where to fly next. You can see they have some sort of logic here for localizing. And in the digital twin, you can see they did the best. And 10-minute flight, they had less than 3-meter error. And University of Georgia team, they also somehow figured out the tentative direction and did a circular flight. So all of these are possible. You can test if you have your own AI-based or other heuristic algorithms you can deploy and test. So the point here is you have some wireless KPI, you decide how the drone flies, and this can be done with multiple drones. It doesn't have to be a single drone. If you have 2 drones and they are somehow communicated, this becomes an even more interesting problem. Maybe that can be one of our future challenges. Our second competition was Autonomous Data Mule Challenge. There are 4 towers that have certain amount of data. The drone has to fly as quick as possible and then land back after collecting the data from all the 4 towers. The problem is the drone doesn't know how much data is available in each tower. So we reveal that to the drone whenever it comes up to 25 meters, and then it has to figure out how to fly and how to collect data. So this was the what I referred earlier, that we had 22 teams registered, and 16 of them, they submitted their solutions in our digital twin environment. And we have these 4 winners. And we are actually publishing the data set portion of these. The individual teams, they are encouraged to publish their own solutions, and some of them they publish, some of them don't. But we have a joint paper with all the finalists. Actually, for this one, we are working with all the 11 teams who submitted their solutions to testbed. as the finalists, we are having IEEE dataset description papers. We collected a lot of additional data here actually with a radar, with RF sensors, with LoRa. While we were doing these experiments, we added additional hardware, and we have multimodal data in addition to USRP. And just a quick example here, I think this was the Columbia University team. Just 3 different realizations of how much data they are supposed to download. You can see that if one of the towers doesn't have a lot of data, the UAV doesn't fly there. It downloads the data on the way going to another tower from this tower, and then it goes to the tower that has the most data. But if there's 100 megabits, you can see it fly there and then to the others. Somehow ignored this one for this. Sorry, the 43. So I'll talk a bit about our data sets, and I'll skim through some of the research that's possible. So we have, I think right now, 27 or 28 data sets. We are adding new ones, including the one from the second student challenge that we have been compiling for a while. So we are curating those data sets, adding README files, and standardizing them so that they are SIGMF compliant. It's a particular data set format. And if you're interested in any of those, we have a long paper. This is under review, but we are about to submit the major revision, wireless datasets for aerial networks. You can find it under archive. And we talk in a bit more detail in all of these datasets, so you can have better sense of what dataset might be of relevance to your research if you're interested. And we talk about the format and give some representative results and possible ways to use the dataset. I talked about the user manual. I'll skip this, but I mean, a nice feature of the user manual is this is Google site. So in the search, you can search with whatever you are interested. Like if you're interested to learn about our FCC spectrum licenses, you can type it in there and the relevant page will come up. And very quickly about some of the representative results. With the helikite I mentioned earlier, we had 6 different flights, 2 of them in a rural area, 4 of them in an urban environment. And we have extensive data for spectrum observations at different altitudes, and we have published a lot of those, some more in review. But this is everything from 85 megahertz to 6 gigahertz at different altitudes. It doesn't distinguish signal sources, so when we are getting the signal measurement in a certain frequency, it's the total power, right? If you have 10 base stations, you have the total power from those 10 base stations, but I think it's still valuable data. So if you're interested in a specific technology, you can focus on that band and see how the behavior changes with respect to altitude, how does it change over years, how does it change from rural to urban, and etc. This is a representative figure. We actually had a 6th one. We are about to submit the revision of this as well very soon. But this shows the occupancy of many of the 4G and 5G bands at altitudes below 50 meters and altitudes above 50 meters. You can see the occupancy suddenly increases in especially in certain bands, in 4G and 5G and ISM bands, and using different thresholds. Just to give you a sense of the ways that you can use. We have a lot of work using 3D radio environment maps. So we collect data from different signal sources. It can be a 5G base station, 4G base station, LoRa, and then obviously drone cannot fly everywhere. We have certain number of altitudes that we fly, but later on, if you're interested to learn the signal strength or another wireless KPI at a different location that we didn't fly, then you can map it based on the flights that we had earlier. And we keep publishing more papers on this too, but there are a lot of AI-based algorithms like transformers or units that are coming up, and we are also exploring some of those. But we have extensive data that you can use if you're interested in this domain as well. Another related paper, this is another paper we are about to submit the major revision. You comparing 3 of the data sets that have different bandwidths, one of the data sets actually has 3 different bandwidths. You can look at the effect of bandwidth, the location, the AFAR data set, the signal source is a rover versus a tower. So the height of the transmitter is also different. So you can look into how all those different aspects, they can affect your performance. And I mentioned about using transformers. This was just accepted ICC. We are about to submit a journal version of this on 3D radio environment maps. One of the things I missed is, I'm sorry. One of the things I missed to mention is, in addition to wireless KPIs, we also log a lot of the telemetry from the drone, and this obviously includes the speed and location of the drone. And for location, we have RTK, so it's pretty accurate on the order of almost centimeter accuracy. So you have very accurate location stamps for your measurements. But we also log the roll yaw and pitch. So these may affect your propagation characteristics. The antenna might be blocked by the drone's body, or the antenna orientation somehow may also even affect. And we have this one came up in Asulomar last year. We use this roll yaw pitch information to improve our 3D radio environment maps. You can see we can have almost 10 dB improvement in the median error if we use this additional information. I'll skip this, and then we have a lot of work. I mean, these are examples, these are mostly our work that I'm presenting, but examples of how you can use the data sets, or you can develop your own experiment and deploy in the AERPAW testbed. You can either localize a signal source. This is for the AFAR experiment, actually. We deployed an AI-based algorithm using ResNet, and we compared with other teams' approaches. We did much better, but this is obviously after a lot of training based on the data that's already available from the other teams. You had extra advantage. And you can also localize the drone using what you're observing at the towers. And we have, these are the 2 papers I highlighted here. And another paper from Asilomar, and I mentioned this earlier, that during the ADAM challenge, we collected data with a radar. This data set is about to be released soon, hopefully in a week or 2. But there is also data from a radar in addition to the USRP data at 4 towers and RF sensor data that we collected. So all of them are for the same exact trajectory that the drone flies for the 11 teams that we deployed in the testbed. And for each team, we had 3 different realizations for different data volumes. And also LoRa. So we have multimodal data sets based on LoRa, USRP, 4-time radar, and Keysight RF sensor. So you can check our dataset page if you're interested in this. So it may allow, for example, Isaac type of research, doing sensing and communication simultaneously. And in the interest of time, we will skip this just to do maybe 10 minutes or so. But we have a lot of also ray tracing data, including modeling of some of the trees. And then we have comparisons with measurements from Keysight Nemo, I believe, and USRPs. So these are 4, only the 3 of the towers are shown here, but we have the data for both the measurements and ray tracing for all the 5 towers. And one thing I'll highlight before ending is, at the fixed nodes, we have 2 different USRPs and 2 different front ends. So you can see here, the drone is transmitting in all these 3 scenarios, and then we are capturing the signal simultaneously at the 2 different USRPs at the 2 different antennas, right? So they are parallel different front ends. But one thing noteworthy here is at some locations, I mean, this is the same tower, but just 2 different antennas that are spaced maybe by 1 meter apart. You can see that at some locations, the signal strength is similar or the same, like at here and here. But at another location, there is like 10 dB difference on what you're observing at that antenna. So this just also tells that even like a 10-meter spacing, maybe there's some additional reflections happening from the tower based on the specific location of the drone. So there may be a lot of variation. So these are kind of the subtle issues that I was referring earlier. uh, from if you just model this in a like theoretical model, you will say it's the same tower location, and you just say it's depending doesn't depend on the antenna. It's the same power, but it changes based on the drone's location. And then with that, I will stop here. We have about 8 minutes. We have workshops which I didn't talk at all. So we had 3 workshops so far. We hope we will have our 4th workshop. If you are interested in some hands-on training, we hope to do it again next year. So I'll stop here to see if there are any questions.
Okay. Thank you, Ismail, for the presentation. I posted on the chat if there is any question. Maybe people didn't post their question, but if someone has question they want to ask verbally, we have all our PIs in here. We can answer any question.
I think everything was clear. I see a lot of
Maybe,
familiar names as well.
yeah. Maybe everything is clear or nothing is clear at all, Ismail. You cannot tell.
Yeah, maybe I'll pick on Alpan. Do you think this is helpful for your NSA project? Are you interested in using us?
I think it will be definitely helpful. I think maybe because for me the main question is going to be I have my own radios and I modify their own FPGAs, and the question is I'm not exactly sure how am I going to take this and put it in the AERPAW platform.
So we do support bring your own device type of experiments. Maybe we
Mm-hmm.
have to have a meeting to discuss the specifics. We might have to develop a specific portable node that we can
Mm-hmm.
attach our radios.
Mm-hmm.
But those are all possible, so we can discuss details and
Mm-hmm.
um,
And also
so,
the other another question would be maybe the millimeter wave radio. When are we going to do this?
I was thinking about you and I was commenting on that, but I mean, we have the radios ready, but if anyone is interested in those, I mean, we don't offer them as like a general availability feature, but with some development, it might be possible. We don't have the portable node to support them. We have to use maybe the tripods on the ground, and they are not attached anywhere permanently at our fixed
Hmm.
nodes either. So yeah, if there's interest in millimeter wave, and what maybe I'll share my screen to show that briefly in case anyone is interested in those. Uh, uh, so there is this Alpan basically developed the 60 gigahertz version and we extended this, but we have software defined millimeter wave radios from Sivers, and we have, I believe, 10 of them. If any of you are really interested, it may require some development and maybe some additional help from your side, but
Hmm.
the radios is this okay? This is the MIG conversion, but the radios they look like this. We have the 28 gigahertz version of those. I think that there were 16 antennas at the transmitter and receiver, as far as I remember.
Hmm.
But yeah, they do support beamforming, and yeah, we hope to make them generally available, but yeah, we couldn't get to that stage, unfortunately.
Hmm. Yeah.
See, Rudra has a
Yes.
hand.
Yeah.
Yeah, I just wanted to say there's sort of, you know, broadly, I think three kinds of things that we cannot do. If it's prohibited by our current FCC innovation zones and licenses, so the, band and stuff like that, or if it's prohibited by our FAA compliance, or if it's prohibited by physics, like physically impossible. So we clearly cannot do those things or stuff like that. Everything else, we are, happy to try. Some of those are just like that and almost for free because they're built in, baked in. Some of those are very costly and, requires a lot of work collaboratively with, folks like you. Maybe even trying to find a grant or something to fund it. And then there's a lot of stuff sort of in the middle kind of in a halfway point where we have done this, but we have not necessarily seen the benefit of trying to push it to very commodity usable because I mean we don't see the business with that, as it were. So the community kind of we're looking to the community to tell us what would be the things to push at and also to help us in getting those done. And but otherwise, I mean, it's your it's your test bed. The physical space that we have, all the expertise that we have, all the connections that we have gathered as a part of this process are at the service of the community. So we only want to work.
Thank you so much, Rudra. I think there is one question you can take in the chat. Did I see? And meanwhile, while you're answering the question, please check the chat. There is a feedback form. It's just like a 5 minute or maybe less than 5 minutes form you can fill out, and only 2 questions are mandatory. The rest are not mandatory. So very quick. You can take even a minute. But Mina, there is a question from Farhan.
Yeah,
You want to take
I
that?
can quickly address that. So, yeah, we actually had a student last year who attended Cyber Powder. This year there was going to be another student, but he decided to graduate, so he dropped in the last minute. Yeah, we are familiar with Cyber Powder. I think Margaret applied to a similar program, but that requires funding, right? So you have to have funding from NSF to support all your travel and personnel costs. We are interested in doing something similar, but we'll see how the proposals we submitted they shape, and we might offer. Maybe Margaret, do you want to?
Yeah, maybe I can add a little bit. Is we have applied for this one, but it's not going to be full-fledged program like powder program because we are focused more on integrating AERPAW into the classroom. So we work a lot more with instructors and not a lot with students directly. But yes, there can be something coming up in the near future.
I want to also quickly add that to the extent that we can, without asking for extra funding, we have put up a self-paced tutorial parallel system. And Dr. Moshe could talk more about that, or you could just go find out from the AirPow website. And it's just a click away from the AirPow website to go look at the from the user manual. At the very front page of the user manual, there is a link to a self-guided tutorial and which is self-paced. For more hands-on and more in-depth, more like weeks long or month long, as you refer to, that would be amazing. But that would require, us to, just like Powder was able to go get funding for that. Either this thing, cyber training thing comes through or something else. So if you're interested in something like that, or if you're interested in terms of trying to work with us to create such a program, you know, absolutely reach out.
Okay. Thank you, everyone. And you are top of the hour. I want to thank you, everyone, for attending. And please fill the form. As I said, if something is important to do, like this webinar is important to do for our community, for us to bring what we offer to the community. And we just started it and we are learning to do it better. So your feedback is really important to help us improve the future webinar, especially the topics that you want to hear from us. We would love to cover those in the future webinars. But as you all know from the email we sent, this is going to be monthly, every last Friday. Swan, you can correct me if I'm wrong, every last Friday of the month at 10 to 11. And we might change this if we get feedback from the community that this time doesn't work for many people. But if it does, we will like to keep it where it is right now. Thank you so much, everyone, and looking forward to see you in the future webinars.
Thank you.
Thank you, everyone.
Bye-bye.
I think we can stop the recording as well.
Oh, yeah, sure.